Hello, I'm Bryan, and in this short video, I will give a brief overview of SolType, a refinement type system we developed for detecting and preventing integer overflow in Solidity smart contracts. Smart contracts are becoming increasingly popular for financial applications, especially those running on the Ethereum blockchain. However, smart contract bugs are very costly. Large amounts of currency move through smart contracts, and smart contracts cannot be modified after they're deployed. Thus, a smart contract bug leading to monetary losses cannot be fixed in production. Most contracts are implemented in an object-oriented imperative language named Solidity. A smart contract is encoded as an object of a constructor, state variables, i.e. fields, and methods. For example, a token contract might have a method called batch transfer, which a user can call to move funds from their account to several other users' accounts. Ideally, a function like batch transfer should be free of integer overflow vulnerabilities. Otherwise, a malicious user could exploit such a vulnerability to generate infinite funds or drain another user's account. In fact, the so-called batch overflow exploit is one such real-world example of generating infinite funds. According to a recent study, integer overflow accounts for most reported smart contract vulnerabilities. To guard against overflow, developers insert runtime overflow checks using a library called SafeMath. However, several economic factors, such as how users try to minimize the overhead costs of executing a smart contract developers are incentivized to avoid runtime checks when possible. But this increases the likelihood of introducing overflow vulnerabilities. Smart contract developers are becoming increasingly interested in using automated formal verification techniques, which will help them detect bugs and statically prove the safety of potentially unsafe optimizations that they make. While a variety of verification techniques are being applied to smart contracts, we believe that refinement types are accessible to non-experts and provide a good sweet spot in terms of expressiveness and scalability. To this end, we developed SolType, a refinement type system that's focused on arithmetic safety in smart contracts. Smart contracts often store numerical quantities, such as user account balances or total amount of currency in circulation, in data structures like mappings and structs. Thus, SolType incorporates refinement terms that express relational algebra-like aggregation properties over nested data structures. In particular, a set of refinement term synthesis rules are used to synthesize sums of nested mappings and structs in a type-directed manner. These sum terms are then incorporated into the typing rules for mappings. In practice, a developer or a type inference tool constructs a so-called contract invariant that holds at method called boundaries. Contract invariants can be expressed as refinement types on a smart contract state variables. These invariants can then be used to prove the overflow safety of unguarded arithmetic operations contained in methods. Similar to previous works such as liquid types, types are refined with terms that can be encoded in decidable logic, enabling decidable type checking with an off-the-shelf SMT solver and optionally decidable type inference based on the choice of inference procedure. To evaluate the practicality of our refinement type system, we developed a prototype tool named Solid that is used to detect when a runtime overflow check is redundant, i.e., the arithmetic operation is overflow safe. Solid incorporates a type inference procedure based on CHC solving, allowing Solid to infer the contract invariant without user input. Solid also includes a semi-automated mode that allows the user to manually provide a contract invariant. We evaluated Solid on several metrics across a suite of benchmark contracts. Our evaluation shows that refinement types are viable for tackling arithmetic overflow in the smart contract domain. Solid is able to statically identify 86% of redundant runtime overflow checks. Furthermore, Solid is comparable to or better than a state-of-the-art automated verification tool in the measured metrics. Lastly, we also show that sum terms and contract invariant inference are important for proving overflow safety in the smart contract domain. If you're interested in more details about our type system, please check out our talk in the main conference. Thanks for watching.